All right, we are in Exploring Creation with Physical Science, 3rd edition, and we're doing Module 3. We've got some terms to learn, and the first one is the law of conservation of mass, and that is matter cannot be created or destroyed, but it can change forms. Sounds like the energy can't be created or destroyed. This is mass. I think of slime changing its form, but it cannot be created or destroyed. But the slime can be created and destroyed. That's okay. So that's the conservation of mass. But how did it get created? It was from other masses getting put together. So I guess there is some truth still in that, right? Law of constant composition is samples of pure compound always have the same elements and the same mass proportions. Just like we were talking about, each and every sugar granule, which is a pure compound, will have the exact same composition of number of protons and neutrons and electrons in every single granule of sugar or atom. All right, the atomic number, that is the number of protons in an atom. And I have so many things I'm going to show you on this. Let's see here. This is a messy and slightly erased atom here. We have the nucleus in the middle with the protons and the neutrons. And around it we have valence electrons that are going around and orbiting around their orbitals. We also call them energy rings last week, but these were the spaghetti in our edible isotopes. Isotopes are atoms with slightly different numbers of neutrons, and so they have the same number of protons but different number of neutrons in their nucleus. So those are what isotopes are. Okay? So when we talk about mass number and atomic number, we're referring to some numbers that are inside of the periodic table. And each and every one of these little blocks, they have three things. They have the atomic number, the mass number, and the symbol. And so for this in hydrogen, the atomic number would be 1. This is the actual number, and that symbolizes the number of protons, and which matches the number of electrons. Okay, and then we have the mass number at the bottom, and the mass number is just the number of protons and neutrons together, added together. So you can know that mathematically you can just subtract the number on top from the number on the bottom, and you'll have the number of neutrons you have. So 0.01 neutrons in hydrogen. All right, so when they want to ask where are almost all of the mass of an atom found, well, the mass is right there. These tiny little electrons are itty bitty, and all of the bulk of the atom is right here in the nucleus. What type of particle is an electron? It's a negatively charged one found outside of the nucleus. All atoms of an element have the same atomic number. Okay, remember, atomic number is the one on the top. So over here, number 18 is argon, AR, and they want to know how many electrons, I don't know if you can see that, how many electrons would be in argon 38. So if its mass number is 38, and its atomic number is 18, how many electrons are there? We talked about the number on top is the number of protons. It's also the same number of electrons. When they ask how many electrons are there, we have it right here. It's 18. Okay? It doesn't matter if this says 38 at the bottom or not. It actually says 39.9, so this must be an isotope of argon because it's only 38 for this mass number. All right, how many neutrons would there be in argon 38? So let's pretend it says 38. The bottom, how many neutrons? Well, what would be the difference? We're going to take 38, we're going to take 18, we're going to subtract them. And we have 20. That's how many neutrons would be in argon-38. If elements have the same number of valence electrons, they're in the same group. So we're going to talk about groups here in a minute. What are the most reactive metals? Alkali metals. I can hardly say it. Alkali metals are the most reactive. Which elements are all gases? D, group 8A. So let's find that on here. Look at it. 8A is the farthest most group right here. Okay? So we have 1A, 2A, and it goes across like that. I stopped writing them down. But we have on page 103 a really beautiful example of the periodic table, and you can see it there. Okay, so now they want you to know some names. Okay, J.J. Thomson's experiments provided what evidence about atoms? It's that atoms contain negatively charged particles. So you want to connect J.J. Thomson with negatively charged particles. So we're going to pretend J.J. Thomson was a very just negative, moody, depressed person who just only thought of negative things, because we're going to remember negatively charged particles, which are electrons. And so that's what his experiments provided evidence about. Okay, J.J. Thomson, negatively charged. Who provided evidence for the existence of a dense, positively charged nucleus in the center of an atom? Ernest Rutherford. All right, so Ernest, we're going to call him Rutherford. How can we remember this? Ernest was eager to find the center of the atom, which was, so we have eager Ernest Rutherford. So if you can try to connect his name with the nucleus, which is where the protons and the neutrons are in the center of the atom. So let's see here. If you hear about oxygen 17 and oxygen 18, what can you say about those things? You can say for sure that those are isotopes, because they have just one mass difference, and that would be the difference in their neutron, right, which makes them isotopes. So the slight differences. Which statement describes how electrons move in Niels Bohr's model of the atom? So Niels Bohr's, he was not boring. Bohr's was not boring at all. He says that they were like planets orbiting the sun, going around and around and around, kind of in this orbital way. So Niels Bohr's was not boring at all. What must happen for an electron to move to a higher energy level? It must gain energy. So you gotta to jump from, see here, from here to here, you've got to have a lot more energy. And really what happens here is, you know that there's only like 2 electrons allowed to be on the first ring, I think 4, 8, like that, something like that. There's only so many. So if more energy comes out, then of course things they have to jump. Valence electrons have to jump their orbitals in order to make room, and they can't have more than so many on each orbital, right? So they have to move as more, and these are the energy, so as more of them, they got to keep on moving out. And so let's see here. What does an electron cloud model describe? Where in the atom the electrons will most likely be. That's what the electron cloud model describes. What is the maximum number of electrons that an atomic orbital can contain? Atomic orbital. Well, the first one, 2, for sure. If an atom of an element has a mass number of 31 and 16 neutrons in its nucleus, what is the atomic number of the element? Okay, let me read that a little slower. We've got an atom. It has a mass of 30. This is really great there. Mass number of 31. That's up here. It's got some symbol. We'll give it a star. And then what is the atomic number of the element? It says 16 neutrons. So we know that in it has 31 protons. Just pretend there's 31 of those. And then it says there are 16 neutrons. Okay, so in that we have the atomic number, and they want to know what is the atomic number. So we know that that would be adding them together. So we have 47. So our this is our little square up here. Our atomic number would be 47. And I totally just said that wrong. Oh, heavens. I thought it was adding. Okay, so I'm sorry. I'm not making this video again. This is take like number 10, I think. I don't know. We've had a lot of troubles tonight. So let's see here. Let me get this right. I'm not going to mess it up again. All right. So mass number is the sum of the protons and the neutrons. I was getting it mixed up with the atomic number. My apologies. So let me get this right. I'm going to write this out. This is the mass is down here. And the atomic number is up here. Boop. Okay, so now I can read this intelligibly. It's really important to get our terms correct, right? So don't let me mess it up for anybody here. All right, so we've got the mass down below of 31. And we know that there are 16 neutrons, so we must subtract from this mass number the neutrons in order to find this number up here. Okay, so we do the math and we get 15, so our atomic number is 15. Then we'll make this our symbol. There we go. All right, let's see if we can do the next one a little better. If an atom of germanium has a mass number, the bottom number, start over, mass number of 70 and an atomic number of 32, get it right, atomic number is up here, how many neutrons are in the nucleus? So now we know we need to, they want to know what's the difference, right? 70 minus 32. Okay? So that doesn't go on this on our periodic table, but it's good to know if we were building a diagram or just wanted to know how many neutrons were in the nucleus. All right, so we're going to talk about two more things real quick. All right, how does the state of the atoms in a neon light change when the neon light glows? And the explanation for this is the neon atoms first must gain energy and then enter an excited state, and then as the electrons lose energy, they return to their ground state from an excited state. So when the neon light glows, it's a change of energy in the electrons, gaining energy or losing energy. All right? So that's the state of atoms in the neon light. A sample of sulfur contains sulfur 32, sulfur 33, sulfur 34, sulfur 36 atoms. Explain why these atoms can have different mass numbers, but they must have the same atomic number. Okay, let's look at this thing again because I'm going to get mixed up otherwise. Get rid of some of this mess. All right, so looking up here, it says, how can they have different mass numbers, but they must have the same atomic number that's up here? Well, we talked about before we talked about isotopes being these kind of things. Like we have sulfur 32, sulfur 33, sulfur 34, 36. All right. What's the difference? If this is slightly different on the bottom here, the mass number is just ever so different, ever so slightly different. Doesn't matter how much or how little. that means it's an isotope if they have the same exact mass, okay? If they have the same exact atomic number. Forgive me, I'm getting those mixed up again. So atomic number doesn't change. The mass number does. It's the difference in the neutrons. It's called an isotope. If they have the same up here, different down here. Okay, we're going to get there together. Don't have this down perfect myself, but we're going to get there. All right. Thanks for learning with me.